I welcome all of you to the class. And as far as today's class is concerned, in today's class, we'll be talking about one more method for solving the nonlinear algebraic or transcendental equations. And today's method is what we call as the Muller's method. As far as the Muller's method is concerned, let's suppose we are having a function y as a function of x, and this function of x is a nonlinear function of x. Okay, that is, let's suppose we have y is equal, some nonlinear function like y is equal to log of x plus 3x square plus 9 cos of x, so on and so forth. Okay, this is one of the nonlinear equations. Or we are having x cubed plus 3x square plus 2x minus 5 equal to 0. Okay, these are both the nonlinear algebraic equations, the first one being the transcendental equation and the second one being the algebraic equation. What the Muller's method says, in order to explain, first of all, the physical significance or how physically the Muller's method work, what we do is, let's say the given function which we have to solve, y is a function of x, is equal to 0, and we have to solve this equation. Okay, so before we solve this equation, let's assume the graph of this equation is y is a function of x. Let's suppose this is our x-axis, and let's assume this to be our y-axis. Okay, and let's say this is our origin, and we also state, let us suppose that the graph of the function y as a function of x is, say, for example, like this. It's like this. Say it's like this. Okay, so if you look at this graph, one of the point at which our function, so I will write this is the graph of our function y is equal function of x, and this is the point, okay, where the value of our function f of x is equal to 0. And in fact, we can say that this point is the point which we are in search of. Okay, that is, let me call this as alpha, and this alpha represents our one of the solutions. Okay, because at this point the value of our function is equal 0. At x is equal to alpha, the value of the function is 0, so this happens to be one of our point. Okay, so how the Muller's method approach? Okay, how the Muller's method work? What Muller method states that if you have a function y as a function of x, what we do, assume a function, take another function, okay, and let that function be g of x, such that the function g of x is intersecting our function f of x at 3 points. Okay, this function is, the second function is the g of function, which we can call as a Muller's function. Okay, we have nothing to do with g of x. We have to solve y as function of x equal to 0. We have to solve y as a function of x is equal to 0. So, and this graph, which is drawn with a pink color, is the shape of this graph. Okay, is the shape of this function. Okay, so what the Muller method states, it states that assume a function g of x and plot the graph of g of x. This g of x is to be selected in such a way that it intersects the function f of x, y as a function of x, at least at 3 points. One is this point, another is this point, and this is the third point. Okay, apart from this, if you look at the first point, draw a perpendicular from this, draw a perpendicular from here, draw a perpendicular from here, draw a perpendicular from here. Okay, so we have perpendiculars drawn. The first point of intersection, this first point of intersection, okay, this is the first point of, what is the x coordinate at the first point of intersection? We call that as xi. Okay, that's called as xi. The second point on the right hand side, the x coordinate, okay, the second point of intersection is having some x coordinate, and we call that as x I minus 1. And the third point of intersection is having the x coordinate that we call as xi minus 2. Okay, fine. And the point of intersection of this g of x with the x-axis, that is this point. Okay, the point at which our function g of x attains the value of 0, or the value of x at which our g of x becomes equal to 0, that is this point. This is on the left hand side of xi. We call it as x subscript I plus 1. Okay, so along the x-axis we select 4 points. Fine, we select a point xi, which is the x coordinate of the first point of intersection, xi minus I, which is the x coordinate of the second point of intersection, and xi minus 2, which is the second point, which is the third point, which is the x coordinate of the third point of intersection. Okay, and on the left hand side of xi we are having xi plus 1. Fine, what is this xi plus 1? This is the point along the x-axis at which our g of x, or the Muller's function, becomes equal to 0. The central idea is this xi plus 1, okay, this xi plus 1 is to be selected in such a way such that this xi plus 1 is very, very close to this function value. That is, xi plus 1 is to be selected in such a way, okay, this xi plus 1 is to be selected, iterated in such a way, or I can say that g of x is to be iterated in such a way such that its point of intersection with the x-axis, that is xi plus 1, gets very, very close to the point alpha. Okay, and alpha is our solution. That's what we are searching. We are searching for alpha. We have to get this xi plus 1 very, very close to alpha. And when xi plus 1, which is a point of intersection of the Muller's function with the x-axis, gets very, very close to alpha, then at that time we can say that xi plus 1 is our solution. Okay, this is how the Muller's method behaves. Now let's see how mathematically this function behaves, how we mathematically solve these functions. Now, as I stated earlier, that the Muller's function is to be selected in such a way that it has at least three points of intersection with the given function f of x, and it intersects our x-axis at xi plus 1. We assume let g of x, let our Muller's function be our, we will say let g of x is equal a is a constant, x minus xi plus another constant, b x minus xi plus c. Okay, call this as equation 1. X is an x coordinate along x-axis, and xi, we know what is xi. Xi is the x coordinate of the first point of intersection of the g of x with the x-axis. Okay, and let's say this is our Muller's function. This we say this is Muller function. Okay, this is the Muller function. Fine, such that at x is equal to xi, substitute the value, g of at x is equal to xi becomes equal a xi minus xi is 0, b xi minus xi is 0, g of xi becomes equal c. Okay, because when you substitute x is equal to xi, then a xi minus xi becomes 0 plus b xi minus xi becomes 0, and you are left only with c. Fine, so g of xi is equal to c. What is this g of xi? This is something important. That is, when in the function g of x you substitute x is equal to xi, then the y coordinate of g of x is g of xi. That is, this much is g of xi. But if you look at this value of g of xi, this is also the y coordinate of, this is also the value of the function f of x at x is equal to xi. Okay, so we can write g of xi is equal f of xi. This is also equal to the value of function f of x at x is equal to xi, which we will be calling as fi. Okay, we call this as fi. Let me call this as equation equation 2. In the same way, let me talk about the next point, gi minus 1 at x is equal x of I minus 1. Fine. So it becomes g of x I minus 1 is equal a times xi minus 1 minus xi plus b xi minus 1 minus xi plus c. Fine. And let's call this as g of I x minus I. What is g of x I minus I? This is the value of the g of x at x is equal to xi minus I. That is g of x minus I is this much. This is also the value of the function f of x at x is equal to xi minus I. So I will write that g of xi minus I is also equal, this is also the value of function f at x is equal to xi minus 1. Okay, call this as equation 3rd. Fine. Now let me take the third point. Let me clean some space here. Let's take the third point now. Let me write it over here. We will say now g of I minus 2. Third is g of xi minus 2. Okay, that is xi minus 2 is this point, this one. Okay, that's equal a times xi minus 2 minus xi plus b xi minus 2 minus xi plus c. Okay, and that's equal, that's again g of xi minus 2 is the value of our function at x is equal xi minus 2. So we'll write this the value of function f at x is equal to x of I minus 2. Okay, call this as equation number 4. Fine. Now let's define few parameters. Okay, I'm not in need of this graph now, so let me clean this graph. So what we can do is, let me define few parameters. Let's define the parameters. Define the parameter. We are having, here we have xi minus I minus xi. We define x of I minus 1 minus xi. Okay, let's call this as, let's represent this as by h1. Fine. Similarly, x of I minus 2 minus xi, let's call this is equal h2. Fine. Similarly, we are having, we'll be having f of I minus 1, shortly we'll be having f of I minus 1 minus fi, let's call this as delta 1, and f of I minus 2 minus fi, let's call this as delta 2. Fine. Fine. So substitute the value of these, xi minus xi is equal to hi, xi minus 2 xi is equal to h2. Substitute these values in the equations 3rd and equation 4. Fine. Therefore, we can write equation 3rd and 4, we can therefore write, okay, let me write here. G of x can therefore be written as, in place of g of xi minus 1, okay, this is equal, we can write, let me show you how to write equation 3. Okay, okay, let me clean the space here. We can therefore write equation 3. Okay, you can write from equation 3. What we can write? We can write a into, we have xi minus 1 minus xi, that's equal to h1. So we have a h1 plus This is xi minus 1 minus x1. That's again h1. So we have bh1. Okay. Then we have this c. C is equal to, our c is equal to fi. Okay. So when we move this fi to the right hand side of this equation, we can remove this c here. We can write the c here minus c, and c is equal to fi. Okay. So the c can be taken from the left hand side to the right hand side of the equation. Therefore, we can write this as, this is equal f(x) f of x minus I minus fi, that's equal delta I. Okay. So I will write this as delta I. Call this as equation 5. Okay. Similarly from equation 4, that is this equation, we can similarly write, I will directly write it now. It can be written as, and sorry, the previous equation that we have written, it is the general equation that we have, the general equation that we have written, that there's a little correction out there. That is, let me first repeat it. The Muller's equation is g of x is equal to a times x minus xi. Sorry, there's a square over it. Okay, plus b times, otherwise it will be a linear equation. X minus xi plus c. This is the Muller equation. Okay, we are assuming to be quadratic. Fine. If you don't put it square out here, then this will be a linear equation and it will not serve our purpose. Okay, so what is there? This is square. So every term you have to square here, and you of course have a square here. So you will be having ah square here. This is a little correction I am making. Okay, so as we go ahead from the equation 4, we can therefore write it as, fine, we can write equation 4 therefore as h2 a times h2 square plus bh2 becomes equal delta 2, and we call this as equation number 6. Okay, now you see we are having two equations. We are having h1, a is some, h1 is constant, h2 is also constant. Okay, because this is the difference between the x coordinates, which always will be constant. So we can rewrite all these equations. Let me clean the entire drawing. Therefore, we can write the entire equations, equation 5 and equation 6, as h1 square, which is a constant, multiplied by a, plus h1 b is equal to delta 1, this equation 5, and h2 square and h2 square a plus h2b is equal to delta 2. Okay, this is our equation 5. This is our equation 6. If you solve for a and b in these two equations, we need to find the value of a, we need to find the value of b, and we are having two equations. Therefore, I will directly write here by Cramer's rule. Let's use the simplest of all the rules. That's called the Cramer's rule. By Cramer's rule, we can find the value of a and b. By Cramer's rule, what you need to do, or you can use the method of elimination. Okay, any method you can use. This is quite easy. By Cramer's rule, we can find the value of a is equal delta 1 h2 square h2, yes, delta 1 h2 delta 1. So you can even write it. Okay, you can even solve it. If you have to solve, let me do that for you. You can even solve it. You have to multiply equation. Okay, you have to multiply equation 5 by h2 square. You multiply here by h2 square and multiply this equation by h1 square. Okay, and then subtract both the two, you will get the value of b. Fine. Therefore, I will directly write here the value of b, the value of a I will write first. The value of a, if you perform the elimination method, will be delta 1 h2 minus delta 2 h1 divided by h1 h2 into h1 minus h2. Fine. And the value of b that you will find using Cramer rule or elimination method is delta 2 h1 square minus delta 1 h2 square divided by h1 h2 multiplied by h1 minus h2. Okay. Once we obtain the value of a and b, I will call this as a single equation. Let me call this as this equation 7. I will return back to the Muller equation. The Muller's equation is g of x is equal a times x I plus 1 minus xi square minus xi square. Okay, or let me write it properly. For x of I plus 1, yes, okay, so we can write this as g of at x is equal to x of I plus 1. We can write the Muller's equation as g of xi plus 1 is equal a times x I plus 1 minus xi square plus g plus b xi plus 1 minus xi plus c. This is the equation, okay? And what is the value of the g of x at xi plus 1? If you return back to the equation, what is the value of Muller's equation at x is equal to xi plus 1? If you return back to the graph, when we had plotted that Muller's function g of x, and the value of g of x at this point, we had taken this as xi plus 1. Xi plus 1 from the previous diagram is the point at which the Muller equation is equal to 0. Therefore, this has to be equal to 0. Fine. Now, if you substitute the value of a and b in this equation, okay, substituting the value of a and b in this equation, we can write a times, okay, I can simply do it. Okay, that's fine. We can write this as, this is g of a times xi plus 1 minus xi square plus b times xi plus 1 minus xi plus c is equal to 0. Okay. If you look at this equation, this is of the form a x square plus bx plus c is equal to 0, which is a quadratic equation. Okay, and we know the roots of the quadratic equation are x1 comma 2, that's minus b plus or minus under root of b square minus 4ac divided by 2 times a. Okay, so for us, okay, our x is xi plus 1 minus xi. Fine. Our a is this, our b is this, our c is this, and we know the value of a. We also know the value of b. We also know the value of c. The value of c is nothing. It is fi, which we have previously found. Okay. So using this quadratic formula, xi comma 2 is equal to this much. Let's find the value of the variable here. That is xi plus 1 minus xi. Our x is xi plus 1 minus xi. That is, if you use this formula, we can write xi plus 1. Clean some space. Minus xi. We can therefore write this as using this quadratic equation, we can write our x is x of I plus 1 minus xi. X of I plus 1 minus xi is equal minus b. That's minus b is minus b. Okay, that's minus b. plus or minus under root of b square minus 4ac divided by 2 times a. That's okay. Fine. If we do what we call as rationalization, fine. Let me rationalize the entire term. Okay. What I will do, I will take this minus out. So it will be minus 1 by 2a, minus 1 by 2a, and the internal sign will change. That will be b minus or plus. Okay, because I have taken minus out, under root of b square minus 4ac divided by nothing. 2a is taken out. Okay, we can therefore write this as, we can rationalize this as, this is 1 by 2a, 1 by 2a, then b minus or plus under root of b square minus 4ac. Okay, b square minus 4ac. What we can, in fact, we can do it like, if we multiply and divide both sides by, if we multiply and both sides by, okay, if we start it, multiply by b plus or minus under root of b square minus 4ac divided by b plus or minus under root of b square minus 4ac. Okay, we can also write this expression like this. Okay, what purpose it will serve us? Okay, it will serve us a purpose that we can write this as minus 1 by 2a, and we can write this as, this is a minus b into a plus b, that is a square minus b square. That is, we can write this as b square minus the square, and this will cancel, this will be minus b square and plus 4ac divided by b plus or minus under root of b square minus 4ac. Okay, so this b square and b square will cancel, 2a and 2a will cancel. Therefore, I can write the final expression as x I plus 1 minus xi becomes equal to minus 2c divided by b plus or minus under root of b square minus 4ac. Okay, therefore this xi plus 1 I can write xi plus 1 is equal xi minus 2c. We know the value of c, that is fi. We also know the value of b, divided by b plus or minus under root of b square minus 4ac. Okay, this is the value of our what? This is the value of our xi plus 1. Why are we interested in finding the value of xi plus 1? For that purpose, I will return back to the graph. This is our x-axis. This is our y-axis. Okay, this was the graph of our function f of x. We have nothing to do with it. We have to solve it. So then we had assumed g of x. Okay, and this point where our g of x, Muller's function, was intersecting with our x-axis, we had called this point as xi plus 1. Okay, and this is the point which actually represents our solution. Okay, we are interested in finding the value of xi plus 1. Okay, we want to find the value of this xi plus 1. Okay, and want to get this xi plus 1 very, very close to this alpha. When xi plus 1 gets very close to this alpha, such that the difference between them remains very, very small, at that time we can say that our xi plus 1 is our solution. And what is giving us the value of this xi plus 1? It is this function. Okay. Now we want to make use of this concept that we have done, finding the value of xi plus 1. We want to use this concept in solving the nonlinear equations. How we use now this Muller's concept in solving the equations. I hope that we can do that in the next class. So thank you very much.